finally we see photons coming out of the wall, and that's very nice. And I will be reporting on this right now. So overall we'll be having 4 pillars. 3 pillars are being built right now. The second science in Hungary, nuclear physics facility in Romania. Can you hear me very well? Shall I go to the mic? Sorry? Yeah, it's better, yeah? Okay. The ultra-high field science facility is still up in the clouds. We are missing some kind of funding, I would guess between 1 and 1.5 billion to do that. So if anybody has this money in the pocket right now, I would be highly appreciating this. And us, so we started in 2006, 2005 with submission. Then we had the preparatory phase. Now we have the 3 implementation. And we are getting online now. And I will be talking about that. And we will be governed at some point. This is the delivery consortium. We will be governed with the so-called ERIC. We have submitted all the documents to do that. And we should be able to generate this ERIC, which is called European Research Infrastructure Consortium. That should be ready by this year, and we have a common umbrella on the whole system. So if you would do proposals, you would send that to one entrance point in the web, and then being distributed in accordance to your needs to the facility which is best suited for you. On the other hand, if you like to do certain experiments in Prague, we wouldn't mind that you become our customer if there's a similar capability in another place. So yeah, you can choose from a number of parameters which you like, physics and societal, let's say, entertainment and other things. We are down here in Dolní Břežany. That's 15 minutes from the airport, 20 minutes roughly. We are outside Prague. This comes with a funding scheme. The funding scheme, when you use infrastructural funds, then it's 85% EU infrastructural funding and 15% state funding. If you are inside Prague, this reverses. So it made sense to go outside. Just a micrometer, 1 step, 1 micrometer beyond the border was enough, and we found this wonderful place, Dolní Břežany, which is owned by the Archbishop, the castle here, this is the Archbishop Castle, and he sold us the land. And he's a very clever guy, and he has now also transferred this hotel into a 4-star hotel. Next time he'll be coming to a 4-star hotel. I think he has even a star in his kitchen, as far as I know. So that's another point I'm making for you to come. And of course, the concept of buying this land was not easy, because we had a contract size which couldn't be signed by the Archbishop or the Czech church, so we had to go further on. So we translated all the stuff, all the letters, and sent it to Rome, to the Vatican. And so the Pope actually signed our contract, that at this time was Cardinal Ratzinger. And with that signature, he also blessed us. So then this contract went back to Czech Republic, and then it was, of course, we bought this land, and we were blessed again. So if you come, you're not only entering a nice environment. At the same time, you'll be using doubly blessed photons, which is a complete different concept. And they look completely different. They are much more stable and much more enjoyable. Okay, can we start the video, please? Yep. Okay, this is how the facility looks like. The entrance hall, so you're welcome to look at it. This is here's the music school, and the mayor is sitting here, so we're in the center of the city. The overall building with the area, this is the converted hotel now. And you see here, this is the laser bay is actually this one here. So this is west, so the sun goes down here. And the office buildings are here. And we have Hyles here close to us. So this is all ready and being completely equipped now. And we are called those ELI beamlines, the high energy beam pillar, which comes from the fact that we are using high intensity radiation to do different things. I want to set the stage for the intensity range of the science we are using and we are doing, and also for the user program. So we're talking relativistic interaction, and you can easily calculate. Most of you know that, but for those of you who are not dealing with relativistic intensity every day, it's a laser who works with a field E on the length of one wavelength. And if this field is strong enough, you can convert that into intensities here easily, then you generate a work which is comparable to the rest mass energy of the electrons. Then you call this relativistic intensity. And this, if you transfer this from here to here, you end up at 10 to the 18 watts per square centimeter. ELI came to life because we were saying, and you know Georg, he's a very visionary person, and he said, okay, we will be allowing the machines to go to the ultra-relativistic regime. That means we go to when the protons are being put in this equation, and because it goes with a square, you end up at 10 to the 24. That was said when we made the application, that we are able to generate up to the 24. And we are not so far from that. I will be showing that to you now. But if you go on and you replace now the wavelength of the light with the Compton length of the electron, then you go into the quantum world. And that means if you calculate this now, you end up here at 10 to the 29 watts per square centimeter, which we are very far from. But this is where you would ionize vacuum. So you essentially would tear apart vacuum and generate electron-positron pairs, which are kind of this picture of Dirac, that you have a Dirac sea, the electron-positron pair virtually coming and going. And when you're able to ionize them, then you would generate them coming to real world. And I think we are having ideas how to get there. And that was why ELI also came to life. So this I borrowed from one of the journals. And so the idea was so you just synchronize many lasers, get it into one point, and then rip apart the vacuum. And then the first thing which will be happening is that some housewife will be coming in Donny Brezhny and ask us whether we will be generating black holes and eating the whole music school. And that is the kind of argumentation you have to have that is highly localized. It would be a wrong investment, 300 million, and then you eat your own facility with a black hole. I will not go to that because that is the idea why you can, with a relativistic beam, why you can accelerate. It's quite simple because the B field becomes very important, and the B field means that you have a component which pushes the electrons forward, and that means you are separating the electrons from the ion clouds. So the electrons are much more flexible. And that means you have now a very strong capacitor. And if you inject an electron by different means, but I'm not talking about that, it could be self-injection, it could be external injection, then you have an accelerator which can't break because you broke everything. Everything is broken already because it's a plasma. So you don't have to worry about destroying things. And that means you're getting fields as strong, static fields as strong as a laser field. So that is the magic of acceleration with electrons. And that was shown then in experiments many years ago. And right now we are around 10 GeV. This is an older slide. So beams of 4.2 GeV were generated, and the length of the accelerator is 9 centimeters because you start to use kind of devices which are guiding your pulse. Anyway, you can also do that without guiding, but then the quality of your beam is not as good. Anyway, this now is being done up to 35 centimeters guiding, and the guys are getting close to 10 GeV. So 10 GeV, a normal accelerator, you would go hundreds of meters. The European XFEL has 17 GeV and has a length over 1 kilometer for the accelerator. So what we are doing, science case, and what is the combination of laser sources, and it comes to the topic of my talk really. So we have different research programs, from lasers to acceleration, to X-ray generation, to biology, to high field. How you can conceive a facility and how you integrate all this stuff to be able to serve users of different fields. It's a very complicated task. And many of the things we simply did not know at the beginning because they are very complicated. What about the specification of your building? You know, building guys, they like to have their own imagination what they are doing. They are building a building and they want to get their money back, or your money for that, what they have done for you, but they don't care so much about science. So to get them to do the right requirement specification followed is a very, very harsh task. And we went through many, many ups and downs to do that. And I think it's one message to Ralph. I think never, ever trust those guys from the buildings. You know, they have to show everything. What they have done is really in accordance to the specifications. But the specification document is 750 pages long. So don't forget this. So there is a lot of work just in the building. So how we have all this, so now the challenges for integration are coming. Everything under one building, under one roof, lasers and their timing, switch yards, beam transport, beam lines, end stations with largely different requirements, local and central control systems, interfaces, and this all needs to be in a safe environment. So this is this task which took us so long to accomplish, and we are seeing now the first light coming, and I will show you that. And so we have the lasers all synchronized to one clock, and then we have the pulse switch yard, and the switch yard brings the laser beams to the different areas. And those are reflecting more or less this is a science program. So how it looks like in the facility, so we have, because as I told you, we have this positively estimated land from the church. We also were very lucky because when we got the lot, there was a rock underneath. We didn't know that. And the rock made this whole thing extremely stable. So when we started to investigate the stability and the vibration behavior of the building, we were completely amazed what we did there. I think you can even do some mirrors on the walls and you would do gravitational wave experiments. I'm joking a little bit, but it's extremely stable, and there's over 30,000 tons of steel bars in it, which is more than the Eiffel Tower. Just, I think you guys made it now to the finals, as semifinals, about the Eiffel Tower. And we bring this beam down with different possibilities for the different lasers. I will just show this shortly, how the lasers look like. Those are the lasers we are having. So the kilohertz, which we built ourselves, then the one which Christina mentioned, and the 10 petawatt laser. So Christina mentioned the 10 hertz laser. All they are based, those three are based on dipsol technology to be as stable as possible. This one is not, because it would cost 10 times ELI to build it with a kilojoule and being pumped by diodes right now, because diodes still not as cheap as you would guess they are. So we integrated all this, so we have available now over 30 millijoules per femtosecond pulses with a kilohertz. This is how it looks like, and we start operation with that. In September, we start with kilohertz high harmonics and hard X-ray sources, and we are driving synchronized soft and hard X-ray sources at the same time. And in principle, this enables electron and ion acceleration at kilohertz rate. I think this is really the laser where you can investigate the fundamentals for industrial applications. because I think just this is coming up, and I guess at some point we'll be having 20 to 30 MeV kilohertz ion beams, which would be changing the picture completely for the applications. Okay, this Hubble's laser was mentioned by Christina. Is Christina still here? No, she left. So I think we changed this a little bit. Maybe at some point we come back to this one with the kilowatts. Right now this laser looks like this. And we had last Friday the inauguration of the system, and we have done the first shots. It's amazing what we got. The pointing was better than 1 microradian. The stability is less than 1% RMS. This is where we had the button, the push button, and then we had to explain to the politicians what to do. So typically when you inaugurate someone completely let's say, not even having any clue of lasers, is pushing the button and you explain what is happening and that the universe is going to survive after that. And we did it, explained it to them, and the politicians were really able to push this button. That was amazing. And this is a kilojoule laser which comes to us in a few weeks. It's now at 1 kilojoule 1 shot per second, and we'll be compressing it. We have done the experiment demonstrated the bandwidth compatible with 120 femtoseconds. So now remains to compress it. This is a little compressor, a little locomotion we call it, or you can also say submarine is 18 meters long, 4.2 meters in height. Those are the active elements, and that's all being the installation starts somewhere in summer. So we are quite convinced that we will be having, by the end of the year, we're having the kilojoule running, and then we do the compression within the next year. So we will be having 10 petawatt, 150 femtoseconds, 1.5 kilojoules. We do X-ray generation. There was some introduction just recently. We use different ways of doing it. One is directly, we're firing the laser directly on the solid target, generating just K-alpha radiation by driving fast electrons into the material, generating the vacancies, and then there's this fluorescence coming. So it's a K-alpha source, typically in the range between 10 to 30 keV. Then we do high harmonics. They could be different. They can easily go directly from gases. It's one version, but we are more interested because we have more power available. When you do that in gases, it's typically at 10 to the 15th watt per square centimeter, which is for us kind of, let's say, not very challenging, let's put it this way. So we really want to go to relativistic interaction. So we can do that also with solids. So we shine the laser on solids because we have 10 to the 19, 10 to the 20 watts per square centimeter. And what happens there, then you get very, very short pulses in reflection like high harmonics, which are typically in the attosecond range. And if you do it right, they are single pulse attoseconds, but the conversion rate is extremely high. So from the simulations, what we see, you are really competitive with big other facilities, and you're talking attosecond pulses here. And we do this, and the major baby we are having is this Lux FEL, which we will be building in this area here, which is laser undulator radiation. I just want to show that. This is how this experimental area looks like right now, so it's ready to go. And this is the L1 laser, and we have some backup lasers, so we can do experiments with different end stations, but I don't want to go into details here. So you can do solid state material research, you can do atomic molecular science. We have all the end stations ready. They are all commissioned, and you are welcome to come to submit your proposal. The undulator radiation machine we developed with Hamburg University together and with DAISY. And they have demonstrated, we have a contract with them, they have demonstrated now water window radiation coming from undulator by driving the electrons from a laser, so laser undulator radiation. And they are single femtoseconds, we are measuring it right now, and they are optical perfectly synchronized. And this is just a transmission grating measurement. Now we are at 4 nanometers, so we are really entering the water window. That was always our wish, to go to the water window, to claim something to the biologists, that we are important to biology. So this also they had a 24-hour continuous operation. That is the image I got from Andy Meyer here with the Angus laser, which is in DAISY. And they have shown that you can run this almost like an accelerator facility. I think it was really a breakthrough. The next step is now, of course, to enhance, and we all said that, to enhance the repetition rate. But those are other lasers, and also other Hubbard's laser. And so we had that from the beginning on in our white book to come to a tabletop kind of FEL machine. And we have done this now in more, let's say, detailed way. So that should be a test bed for the FEL, and that we do the design studies within Eupraxia. The stability requirements for the integration are coming from a stable laser driver and also from a very important new beam transport concept, because you bring always a laser from somewhere to somewhere, and it's not always short. So you still need to have a very stable transport concept. Of course, the building stability, I talked about it. And of course, the Hubbard's laser is the one which we are used. Our building is, as I said, by God given, very stable building. You see here at 10 hertz, we have roughly a nanometer offset, which is really amazing for such a building, such a huge building. This is how it looks like. We bring that in this transport system to the different area, and it looks, unfortunately, has the longest way. The laser comes in here and then goes here to that area where the undulators are standing, but it's how it developed. But the required stability is extremely high, so we need really microrad, but microrad of stability, of pointing after the beam transport. So if your laser has 1 microrad, your error budget is 0 for your beam transport. So we negotiated that and say, okay, let's talk about 2 microns. No, we couldn't go, so we designed it in a way that we have less than 200 nanorad per bound stability to be able to do that. This is how the laser works now. It's 16 joules, 28 femtoseconds, 3.3 hertz. It will be ramped now to 10 hertz. It's very nice. And we built those beam transport things which are really reflecting a kind of repeating what is the building doing, which we were aiming at, because the building is extremely stable. Idea is very simple. And now we have this demo FEL experiment, which we are building. I mean, I don't want here, this I think the audience knows very well about that. The compactness of the FEL in principle comes from the fact that the peak current of your electron bunch is extremely high because of the shortness of the pulse. And that makes the whole SARSI length very short. So we have just to show it in the case A, which is the long wavelengths, we need 300 MeV, and we can go down with a saturation length of 2.1, 2.2 meters, which is amazing for getting this going. If you go to 1 GeV in a water window, you need roughly a length of 8.59 meters. So if you put that all together, it's a design study which we did for Eupraxia. You see that saturation length can be reached within 10 meters, but that is not just the length of the undulator, but is all the undulators together in the length. And so we have this building. This building is over 110 meters long, and we've foreseen this acceleration length, so we can build FEL end stations and work with Eupraxia on all the details, what we need to build the facility within UPrax. I think it's a wonderful test bed. Okay, at 10 Hertz, what we want to do is Hubble's. We want to go at 10 Hertz. We might have 10 to the 13 brilliance, and we would be quite amazingly high with 10 Hertz somewhere here at 10 to the 13 for brilliance. This is how, can we run this quickly, this video? Hope it's working. It doesn't seem to work. Oh yeah, it does. So how it comes. So you see one of them is the undulator radiation source here. It looks to be extended then further on. And that is the HEL, we call it high energy electron acceleration beamline. So we have them both in one area. That's to be able to do work together. And when we talk to the church, we don't use this acronym. Okay, I think I'm more or less done. How this all looks like, I have many words. One word about, we also do ion acceleration. This is the ion accelerator that's being built right now. In ion acceleration, the problem is always you need to have a very high contrast of your laser beam, because any kind of pre-pulse will generate a pre-plasma, and in a pre-plasma, you don't interact really with the solid state material where you want to accelerate. So you interact with the pre-plasma. So you want to control the level of pre-plasma very well. And we do that by having those plasma mirrors. So the laser comes with 10 to the 11 contrast, peak to picosecond pre-pulse. And we need to go to 10 to the 13. It's very easy because you go to 10 to the 20. And if you go to 10 to the 20, 10 to the 21 intensity, you don't want to have pre-pulse intensities which are above 10 to the 10. So it comes from there, from this consideration. Okay, so we are aiming at 10 to the 9, 10 to the 8 in pre-pulse. With different stages you can use. This is actually being done right now, as I said, and this is taken last Friday. So the whole beamline is in there with all the magnets. So the beamline is doing the following. You can generate ions up to, this machine is designed to be able to use up to 300 MeV ions. But because you have this magnetic chicane here, you can also tune the energy of the ions because they're typically coming with a certain energy spread. So you tune that with a slit, and also at the same time you're also changing the energy spread. So we can go up to 5% energy spread with up to 300 MeV. We tested this whole beamline on an accelerator, and it's all working. Okay, that's all installed, and it's just waiting for the laser. This is what this thing can do. When you go to higher repetition rate, of course, you need higher repetition rate targetry. Right now, we are working very concentrated on so-called hydrogen ribbon, which is a hydrogen ice target, which is a ribbon. And we have done the first experiments at RAL with that ribbon, and we go easily to 50 to 60 MeV ions with the RAL laser. Okay, and that is, I'm coming to the end of my talk. This is a very important message here. So when we met the owner of the local brewery, which is right just behind the bottle, a little bit further to the left, and he said, okay guys, you really inspired me, and I do laser beer. So usually when you come to us, you have to drink laser beer. The importance of this beer is that it hasn't laced yet. So I promised him when we have the 10 petawatt that we take one of the bottles and get it to lace. Thank you very much for your attention.